Hello everyone, this is Oshani from Chinta.com. Today we will solve a very exciting problem. It uses complex numbers and binomial theorem together. It's a very exciting problem from ISI BStat BMath Entrance, but problems like this have come in many mathematical olympiads. So it will be a very enjoyable experience. Also, I wanted to share with you another news of my personal life. I just switched back to this dumb phone, that is a phone without internet or Android or iOS. So if you notice that the amount of time you spend on your mobile device, it's about 2 to 6 hours every day, and you pick it up every so often just to check for updates. This creates a lot of distraction and you lose a lot of time of your life doing this. I was feeling that pain, so I planned and I switched back to this phone. And if you are a student of mathematics, I strongly suggest that you consider this option. Many people all around the world are switching back from smartphones to dumb phones. You can have the smartphone, keep it back at home. You can come back and look into the updates. I will do that because I need some of the updates from WhatsApp and email and other things. But I plan to keep that in my home. I spend so much time telling you this because I also want my students to take back the time of their life that they're sort of using in the smartphone world. And with that, let's start the problem. Okay. So problem says that n choose 0 plus n choose 3 up to n choose 3k, okay, this is less than or equal to 1/3 of 2 to the power n plus 2. That's what we have to prove. And what is k here? K is the largest integer for which 3k is less than or equal to n. So for example, if n is 20, 3k is 18, the largest integer less than n. So largest multiple of 3 less than n. So k is 6. So it's like this. And I think you are seeing something very curious in this problem, that we are jumping in steps of 3. First we have 0, n choose 0. Then we have n choose 3. And like this we will go on. The next one will be n choose 6, okay, and you go on up to 3k. You go on up to 3k. So we want to show that this is less than or equal to 1/3 into 2 to the power n plus 2. There is so much to learn in this problem, so I strongly suggest you grab a piece of paper and pen and follow along with me, and I'm sure we will learn a lot. All right. So the first thing is that this steps of 3, whenever you see this, think about cube roots of unity. Cube roots of unity. So if you don't know what is a cube root of unity, it's simply a number whose cube is unity, that is 1. A number whose cube is 1. So its solution to the equation x cube equals to 1. What is that number whose cube is 1? Well, 1 itself is one such number, but there are 2 other complex numbers whose cube is also 1. So let's figure that out. So x cube is equal to 1 implies x cube minus 1 equals to 0, or x minus 1 times x square plus x plus 1 equals to 0. So this part tells you that x minus 1 is 0, which means x is 1. So that is one of the roots, one of the solutions. The other solution is you have to solve this quadratic, x square plus x plus 1 equal to 0. So I will use the quadratic formula. What is that? That's x equals to minus b plus minus square root of b square minus 4ac by 2a, right? So here b is 1, a is 1, and c is also 1. So here x is equal to minus 1 plus or minus square root of 1 minus 4 times 1 divided by 2 into 1. So that is minus 1 plus minus square root of 3i by 2. This is square root of negative 3, which is square root of 3 times I, the imaginary number. So the two other numbers whose cube is 1, is sometimes in literature they are known as omega, which is minus half minus plus square root of 3i by 2. And then the next one is sometimes known as omega square. So you can just check. If you square this thing, you will get the other number, other root actually. Minus half minus square root of 3 by 2i. So this is something you can check. Take this complex number, square it, and you will see that you will get this other number, which is the other root that we got from here. So these are the three cube roots of unity: omega, omega square, and 1 itself. And if you plug in omega to this equation, x squared plus x plus 1, of course omega satisfies this equation. That's what we found by solving this equation. So omega square plus omega plus 1 is equal to 0, or 1 plus omega is negative omega squared. 1 plus omega is negative omega squared. So this is an equation that we will be using a lot in this particular problem. In fact, I will show you a geometric presentation of this. If you take the circle, unit circle, and draw the x-axis and the y-axis, then I can actually show you the three roots of unity. There are 3 points on the plane. The first one is this one, which is 1, 0. That is the first root that we got, 1. Okay, so it's not really 1, it's actually 1, 0. So if you have learned complex numbers, for example, in our mathematical Olympiad program or in ISI CMI entrance program, check the link in the description for those programs, then you know that complex numbers are really points in the plane. They're points in the plane. So 1, 0 is one of the points, and then you have this one, which is negative half plus root 3 by 2i, and the third one is this one, which is negative half minus root 3 by 2i. Negative half minus root 3 by 2i. So these are the 3 points. They are on the unit circle. So their lengths, I think in my notation, the first one is, this is omega, and this is omega square. Then the modulus of omega square, modulus means the distance of omega square from the origin. This is 1. I mean, of course, you can, do the Pythagorean theorem thing, and you can also check that's 1. But geometrically, it's 1 because it's lying on the unit circle, and the length of the complex number from the origin, the distance of it, that's the modulus. So omega squared is 1, omega is 1. In fact, any power of omega is also 1, the modulus. Why? Because you are just rotating that many times, like n times, but rotation just changes the angle, so it changes the position of this one, but it does not change the distance of the point from the origin. The distance remains 1. So any power of omega, the modulus of that is 1. So one last thing that we will need is that real part of a complex number is less than or equal to the modulus of the complex number. And that's very simple. What is the real part? So if I take a complex number, it's just a point in the plane. Let's take this point in the plane. Then let's drop a perpendicular and join this hypotenuse. Then this length is the modulus of the complex number, the distance of the point from the origin. And this length, I'll do it in red, this is the real part of the complex number. The real part of the complex number. So certainly hypotenuse is larger than one of the sides of the right triangle. So real part of a complex number is less than or equal to Z, the modulus of the complex number. So we have all of these tools in place, and we will use this to solve this problem, which initially it doesn't look that it has anything to do with complex numbers. So let's see how it all works out. So we'll start with a very simple binomial expression, 1 plus x raised to the power n. Okay, so what is this? This is 1 plus x. Actually, let me write it a little bit differently. N choose 0 into 1 plus n choose 1 into x plus n choose 2 into x square, like this, up to n choose n into x to the power n. Right? So that's what this expansion is. If you don't know binomial theorem, I suggest you look into some algebra book. Binomial theorem is a very, very important tool in algebra. For example, a plus b whole square is a square plus 2ab plus b square. This is also binomial theorem, but in a very small, contained manner. It's in a very contained, very easy situation. This is a general case. What happens if the power is n? Okay, so now what I'm going to do is I'll just replace x with omega. Remember omega, the complex cube root of unity, that is negative half plus square root of 3 by 2 I, this particular number. I'm replacing x by that. I'm replacing x by omega. This is a very neat trick. We use it all the time in different type of Olympiad problems and Math Olympiad and ISI CMI entrance problems. So you should learn this trick, okay? So once we do that, we have 1 plus omega raised to the power n. 1 plus omega raised to the power n is equal to n choose 0 plus n choose 1 times omega plus n choose 2 times omega square plus n choose 3 times omega cube. But omega cube is 1 because omega is a cube root of unity. So if you cube omega, you will get 1. So that's just 1. So this thing is simply 1 plus n choose 4 omega raised to the power 4. But omega raised to the power 4 is just omega cube times omega. But omega cube is 1, so that's just omega, right? So it just repeats like this. So n choose 4 times omega. So I'm just going to write the reduced form. N choose 5 times omega square. Well, actually it's omega to the power 5, but you can split it into omega cube times omega square, and omega cube is just 1, so omega square is remaining. N choose 6 times omega to the power 6, which is again 1. So we'll keep on doing this up to n choose 3k omega to the power 3k, but that's also 1. and you can probably go in up to n choose n omega to the power n, and then we don't know what is omega to the power n. That's fine. That's all right. We will see that that won't matter really. Now, I'll remind you that we talked about 1 plus omega, this particular thing. What is 1 plus omega? Well, 1 plus omega is negative omega square. We have already found it before. We talked about this. So let's use it here. So that's simply minus omega square whole to the power n, or negative omega to the power 2n. Negative omega to the power 2n. Okay. So that is equal to n choose 0 plus n choose 3. I'm just clubbing the same terms together. Okay. N choose 0, n choose 3, n choose 6. These are all having numbers 1 multiplied to it. Omega cube is also 1. Omega to the power 6 is 1. So all of these up to n choose 3k plus n choose 1, n choose 4, like this, up to omega. These all, so I'll take omega common. So n choose 1, n choose 4, n choose 7, for example. So from all of these things, I can take omega common. So omega is taken common. And then I have n choose 2, n choose 5, like this. From these, I'll have omega to the powers 2 as common. So I have sort of split everything up into similar looking groups. And this is actually the fun part. I have sort of crystallized out the base 0, 3, 6, 3k into one part. This sort of shows that we are going in the right direction. Okay, now what I'm going to do is I will calculate the real part of the right hand side. I will calculate the real part of the right hand side. Okay, so let's do that. The left hand side, the modulus of negative omega to the power 2, and the modulus of it is just 1. I told you any power of omega, the modulus of it is 1, and negative of that is also the modulus. The distance of the point from the center would always be 1. So this is 1, which is greater than equal to the real part of the right hand side. The real part of the right hand side, this particular thing. The real part of the right hand side. Okay, so I will calculate the real part of this particular quantity. So first I have this n choose 0, n choose 3, up to n choose 3k. Then I have n choose 1, n choose 4, and this is negative half plus square root of 3 by 2i. And then I have n choose 2, n choose 5, negative half minus square root of 3 by 2i. Okay? Alright, so I can now split the material and conclude that this is n choose 0 plus n choose 3 up to n choose 3k. And then I can take one negative half common, and I will have n choose 1, n choose 4 plus n choose 2, n choose 5, this thing. And of course I can then take root 3 by 2 I times n choose 1, n choose 4, like this, minus n choose 2, n choose 5, and so on. Okay, so I'm almost there. I'm at the last step. In fact, what I'm going to do is I'll just add a half times n choose 0 up to n choose 3k, and I will subtract a half times n choose 0, n choose 3, n choose 3k, like this. So you will immediately see why I did that in a second. So now this part, we have 1 times n choose 0, n choose 3, n choose 3k plus half times n choose 0 up to n choose 3k. So we have 3 by 2 times n choose 0, n choose 3, n choose 3k, and negative half times n choose 0 plus, now I can just write n choose 0, n choose 1, n choose 2, n choose 3, n choose 4. So all the binomial coefficients coming together. N choose 1, n choose 2, all of it. And I will completely ignore this thing because this is the imaginary part. This contains I. So I'll completely ignore it. Okay. So this is the real part. This is the real part. And we know that it's less than or equal to the modulus, which is 1. The modulus, the distance of it from the origin. So just multiply by 2 on both sides. And of course, notice that this is 2 to the power n. Sum of binomial coefficients, sum of all binomial coefficients from n choose 0 to n choose n is simply 2 to the power n. So if I multiply by 2, what I have is 3 times n choose 0, n choose 3, n choose 6 up to n choose 3k minus 2 to the power n is less than or equal to 2. I just multiplied by 2 on all sides. And I am done because I can just take the negative 2 to the power n to the other side and divide by 3. So n choose 0, n choose 3, n choose 6 up to n choose 3k is less than or equal to 1/3 of 2 to the power n plus 2, exactly what we wanted. All right. So I think you learned a lot from this problem, how to use complex numbers in the context of binomial theorem, and how to split into real and an imaginary part and apply the complex inequality in this context. If you like this sort of problems, please consider subscribing, liking, and commenting in this video, and share it with your friends. And I'll come back to you with more problems. Stay away from smartphones if you can, and keep on doing great mathematics. Bye. I'll see you in the next one.